This new section, we're going to be talking about arcs of a circle. And there's a number of definitions that we need to get out of the way. The first being, what's an arc? Well, the arc is part of a circle, a continuous part of a circle. Here is a circle, perfectly round circle. Basically, you pick 2 points on the circle and you go like that. That's an arc. This is an arc. You take 1 point of a circle and another point, and you connect the 2 dots by going around the circle. That's an arc. You cannot say that those 2 combined is an arc. Those are 2 arcs. So that's an arc. Again, you have a circle. Pick any 2 points on the circle. Go from 1 point to the other. That's an arc. What's in red? Let me draw it again. So what's in black is an arc. What's in red is an arc. This portion here is an arc. This is an arc. What's in black there is an arc. Go from 1 point along the circumference of a circle to another point on the circle. Unlike a chord where it's a straight line and it goes inside the circle. There's something called the central angle. Excuse me. You have the center of a circle. And you draw 2 radii. You have this angle here. That is called the central angle. That is called the central angle. You have this circle here. You have an even bigger angle. This arc, central angle. That's the central angle. I suspect that if this is the center, it always has to be from the center. If you want theta to be that distance, you want the angle to be that, well then this is the central angle. It has to, the angle has to, the vertex of the angle has to be from the center. In other words, if that's the center, and you go like this, this is not our central angle. In fact, maybe what I've been saying was a little bit wrong. See if we can go back. Okay. Sorry about that. Basically, let me just draw it over here. Had nothing to do with arcs, I'm sorry. That's the central angle. That's the central angle. It cut off this arc, but nonetheless, that's the central angle. Sorry about that. That's the central angle. That's the central angle. In this page right here, that's not the central angle because it didn't start from the center. I can draw one that cuts off the same arc. That angle in there, theta, that's the central angle. Okay? It just starts from the center. That's the central angle. It's the angle. It's not the arc. Sorry about that. I have arcs in the back of my mind for this section. That's the central angle. Now, you have a minor arc and you have the major arc. For example, there's a birthday cake in front of you. Initially, it's not cut at all. It's not cut. And the host, right in front of you, cuts it like this. Puts a cut here, and puts a cut here. Well, this leaves two pieces of pie. It leaves this big piece, and it leaves this little piece. Naturally, you assume that you're supposed to get the little piece. Okay? And so here's an angle. What we call this is the minor arc. This is the minor arc between those two. The major arc is the arc that starts from here and goes all the way to there. What's in black, that's the major arc. This is the major arc. That's the major arc. If you have this circle, and that's the center, you have this nice big angle here. Still, this angle is smaller than that angle underneath. So, we call this the minor arc. That's the minor arc. This here is the minor arc. And the major arc would be that. That is, this here, that's the major arc. It always has to be from the center. That is, this angle must be central. Now, you may say, well, what if the angle is 180 degrees? This is 180 degrees. And so is this. Okay. Doesn't matter which one you talk about. That's an arc and that's an arc. They're the same lengths. Now, if I draw an angle, how do you know which arc we are talking about? How do you know which arc we're talking about? Here's the center, O. I go like this, from A to B. Now there are two arcs. There's that arc and the big arc, the major arc. Now, when you write arcs, like line segments, you have to say the symbol. The symbol is just literally an arc. Now, if somewhere, whoops, I didn't have to do that. If somewhere along the circle is a point X, and you say AXB, that is, what arc are we talking about? The one that goes through A, X, and B. I guess we mean that arc. Rather than saying major arc AB. I mean, we could say major arc AB. But that's a lot of writing. Or I guess instead of arc, you could just write AB with an arc above it. Major arc AB. But you don't want to write the word major. You just put X instead. If between A and B was a point Y, we can say arc AYB. And that would mean, in this case, the minor arc AB. So, if it's not very clear which arc we're talking about, insert a second letter. Like if I just write arc AB, most of you would probably think of this arc, the minor. Fair enough. Fair enough. Let's have a convention. When you don't have an extra letter in it, it means the minor arc. But if we wanted the major arc, we'd have to say AXB. We'd have to say AXB. Or actually write the word major. But we don't. We don't. We just don't. This will mean the minor arc, and not because we have a third letter will this be the major arc, but in this case it is. In other words, AYB has 3 letters describing the arc, but it was the minor arc. Okay, if you have a third letter, you should look. Oh, AXB. Oh, yeah. That's the major arc. So we talked about notation there, the arc symbol above AB and ABX or AXB. And we talked about minor and major arcs. Now, it turns out that if you have an arc, or central angle, and this angle is 30 degrees, then the arc is also theta degrees. The arc is also theta degrees. In other words, if this angle is 43 degrees, then this arc, 43 degrees. So, how many degrees would be in the major arc? Well, you have a couple of ways of doing this. You can say that that angle is 360 minus 43, or 317. That angle is 317. So is this. All the way around is 360. If I didn't make a mistake, 43 for one arc, 317 for the rest. When I add them, I do get 360. If that's the center and this angle is 80 degrees, then that arc is 80 degrees. That is, this is an 80-degree arc. And the rest will be 280. The rest would be 280. Because 280 plus 80 adds up to 360. I guess you couldn't read that, but that's 80 degrees. And it has to be from the center. That's very important. Okay. Now, just because two arcs are the same number of degrees doesn't mean they're the same length. Consider these two concentral circles. That is, they have the same center. This small one and this bigger one. This angle is 70 degrees, which says to me that arc that it cut off is 70 degrees. Remember, that's the center for both circles. And this arc is also 70 degrees. But clearly, this arc is longer than this arc. But nonetheless, we still call it 70 degrees. So notice they don't have to be the same length. They just have to come from the same central angle. And we call them equal. Now, when are two arcs, so this begs the question, so when are two arcs congruent? Well, when are two arcs congruent? Well, if in the same circle, they both cut off the same number of degrees, 18 degrees and 18 degrees, then the lengths of this arc and the lengths of that arc are the same. Call this AB, so that's 18 degrees, and call this CD, so that's 18 degrees. We can say arc AB is congruent to arc CD. And we'll call this circle O. Now, there's another way two arcs can be congruent. If you have a congruent circle, call it circle C. And I'm telling you, circle O, let's try that again. Circle O is congruent to circle C. Circles are defined by their centers, circle C. I'm telling you they're congruent. What does that mean? They have the same radius. They have the same radius. Well, if I tell you, oh, I guess I don't want to use C for the center because I use C for something else. Let's just call it O2. O1 and O2. Just a name. And I tell you that they're congruent and that this is 18 degrees as well. The central angle is 18 degrees. EF, arc EF, is congruent to the two arcs in this other triangle. AB and CD. They're congruent. Okay? Again, if it is not congruent to circle O3, maybe this one is smaller, center is O3, and the central angle is 18 degrees, GH. It is not AB, arc CD, arc EF. They're not congruent to arc GH. This is a bit smaller. It's smaller. Okay? If they come from a circle with the same radii, and they have the same central angle, well then, yeah, they're congruent. Now, if they're both in the same triangle, like in my first diagram, yeah, all the radii are the same. All the radii are the same. So, since the central angles are both the same, then the arcs that they cut off are equal. And for the record, same for the major arcs. The major arcs will be equal. Okay, a lot of definitions here. If you have a circle and you have an 11-degree angle, A, B, call this X. Well, AXB, that arc that is all the way around, that arc is equal to 269 degrees. Well, here is another 11-degree angle, and call this CD. Well, if you go from C to X to D, you go from C to X all the way to D, you have this arc. Okay, everything but this. That's also going to be 269 degrees. So we can conclude that if the central angles are equal, then the major arcs that these central angles cut off are also equal. Again, they came from the same triangle. That is, the radii are the same. And I guess I can rephrase what I just did a moment ago. You don't even really need a central angle. If you have a circle, and from here to there, 50 degrees. If this is 50 degrees, say from A to B, and from C to D is also 50 degrees, then we can conclude that AB is congruent to CD. You don't need the central angle, but if you want it, there it is. That's 50 degrees, and that's 50 degrees. But you don't need that. Now, if it turned out that these two circles that I'm drawing are in fact congruent, that means they have the same radius. And I tell you that this arc from E to F, 50 degrees, we can now say that they're congruent. And say arc, use the arc symbol. But you need to be careful. The circles have to be congruent. And I'm saying they are. Okay? And again, here's the center if you want to see your little slice or bean slice. That angle is 50 degrees. Now, with every one of these sections comes some theorems. In this one, you have a number of theorems. We have 6 theorems, but there's really only 2 or 3 of them. Theorem 1. We can talk about chords and conclude some. We can start over with chords and talk about central angles, and we can start with central angles and talk about chords. If in a given circle or congruent circles, if these two arcs are congruent, if these two arcs are congruent, then so are the central angles. You know what? That's theorem 1. If the chords in a given circle are congruent circles, if the chords are the same length, they cut off the same number of angles, same number of degrees, then the central angles are equal. I mean, after all, if this is 48 degrees, if that's 48 degrees, and it equals this arc, which is 48 degrees, then guess what? The central angles are 48 degrees. And the reverse is true. That's the center. If you have two central angles are the same, 25 degrees and 25 degrees, then the arc that they cut off, these have to be congruent. Of course they are. They're both 25 degrees. They're both 25 degrees. They're both 25 degrees. Again, whenever I say two arcs of one circle or two central angles of one circle, I can also say congruent circles. Okay, like over here, if this circle is congruent to one above, and this arc is 48 degrees, then this angle and that angle are the same. If this angle and that angle are the same, then the arcs that they cut off are the same. Okay, so those are two theorems. If they're in a given circle or congruent circles, if the arcs, if you have two arcs that are the same, then the central angles are the same. If you have two central angles that are the same, then so are the arcs. Now we're going to talk about chords. We're going to talk about chords. If this is one central angle, say it is 15 degrees, and here is another central angle, which is 15 degrees. Their chords must be the same. If the central angles are the same, then this chord and that chord, the same length. It's the same length. It's the same length. Okay? I mean, if for some very, very bizarre reason, I think it's bizarre, maybe I'm wrong, but if you had a pizza pie, and these are two slices, same size. Let's actually make that believable. Same size. If for some reason you get into the so now these two slices are exactly the same. And if for whatever reason you cut off this piece here, well, this length and this length, they're going to be the same. Okay? If the central angles are the same on one circle or two congruent circles, then their corresponding chords are the same. And it works the other way. If you come to know that this chord and this chord, same length, then you better conclude that those central angles are congruent. If those two chords are congruent, then the central angles are congruent. They come in pairs. If the two central angles are the same, then their intersected chords are equal. If the congruent. If the chords are congruent, then the angles are congruent. They come in pairs. So we talked about central angles and arcs. We talked about central angles and chords. Now we're going to talk about our chords and arcs. Again, we talked about arcs and chords. No, actually we haven't. We talked about arcs and central angles. We talked about chords and central angles. Central angles. And now we are going to talk about chords and arcs. If in the same if in the same circle, you have two arcs that are equal, then the central angles are equal. If the central angles are equal in a given circle, or congruent circles, the arcs are equal. If the chords in a given circle or two congruent circles are the same lengths, then the central angles are equal. Congruent. If the central angles are equal, then the chords are equal. Same thing with chords and arcs. If you have a circle, and you know that this chord and this chord congruent, well, this arc and this arc are the same. And one way to do it is to use the two that we've just talked about. If the chords are the same length, that means these angles are the same length. Oh, if the angles are the same angle, the angles are the same, then the chords are equal. If you have two chords, and you come to know that in a given circle or congruent circles, you come to know that the arcs are the same size. Don't worry about it. The chords are the same length. Again, if the chords are the same length, then so are the arcs. They come in pairs. You might want to say in triples. You might want to say in triples. You might want to say in triples. The arcs, the chords, and their central angles of a given circle or congruent circles. They're all the same or they're all different. In other words, if this arc is the same as this arc, okay, that congruent. That means the chords are congruent, and it means that the central angles are congruent. All or none. All three or none. If it turns out that that initial arc and this arc are different, well, that tells me a lot. That tells me that this chord and this chord not the same. It tells me this angle and that angle not the same. Either for a given circle or congruent circles. Those three are going to be the same or they're all going to be different. Again, if you have a circle and you have this arc here, from here to there, you have that arc, and you have this arc over here, and they're the same length. They're congruent. Oh, you mean that that chord and that chord are the same? You better believe it. And if that's the center, you mean this angle and that angle are the same? You better believe it. If any one of them is not true, if this angle and this angle are not the same, well then the arcs are not the same, nor are their chords. All or none. All three or none of the three are congruent. None or all. Arcs, chords, and central angles. one last comment. What you need to remember is, if this is the arc, then when we talk about chords, we mean that chord. And if this is the arc, or if that's the chord, go from the endpoints of the chord or arc to the center. And that's the central angle. So central angle, chord, and arc, they all define the same thing. They all define this area. They all define the same thing, that area, that slice. You can tell somebody, they'll think you're nuts, I understand that. But if you want that size slice, and it turns out that this central angle is 30 degrees. Well, you can say, I want a 30-degree slice. I want the central angle to be 30 degrees. Or you can figure out this distance for a 30-degree angle with the given radius. You can figure out that distance, and you can say, I want a slice that has this chord, and with pencil and paper and this and that, they'll give you the same slice. Or you can say, I want the arc to be 30 degrees. They all correspond to the same slice. The hard one is to find out that chord. But nonetheless, no matter what slice they cut, if they're all 30 degrees, those chords will be equal. So those are the 6 theorems. And we'll do a couple of problems, and like always, we'll move on. All right, so let me erase this, please. So, suppose you're given the following. You're given that's the center. You're given this is A. You're given this is B. You're given this chord. And you're told that this is 20 degrees. And you're asked to find the central angle. Find the central angle. Well, forget about the circle for a moment. Well, okay. Remember the circle for 1 minute. Those two are the same. They're both radii. Now forget the circle for the next moment. If this angle is 20 and these two sides are the same, well then that's 20 degrees. And 20 plus 20 is 40. Well, you have this third angle is going to be whatever it takes to, to add the 40 to get to 360. 0 plus 0 gives me 0. 4 plus 2 gives me 6. And 3 gives me 3. This other, excuse me, I am so sorry, the 2 to 3 angles in a triangle do not add up to 360. They add up to 180. So 20 and 20 is 40. What do you add to get 180? Well, 0 plus 0 gives you 0. 4 plus 4 gives you 8. 1. That other angle is going to be 140. This is a 140 degree angle. The central angle is 140 degrees. Let's do another one. Here's the center. You have one right angle, that's given. And you have a 60-degree angle. A, B, C, D. And you're asked to find various things. You are asked to find the measure of BC. You're asked to find the measure of CDA, the measure of arc CDA, to find the measure of BC. Oh, already said that. BAD, the measure of arc BAD. And also the measure of arc CBA. Well, my way, how I would do this is I would say, well, this is 60, so then that arc is 60. This is 90. That means that arc is 90 degrees. And maybe I should have said that AC, okay, I'll also give you that's 90. So that's 90 degrees. Well, so far you have 90 and 90 and 60 and an unknown, and you wanted to add up to 360. Well, 0 plus 0 plus 0 is 0. Add another 0, you get 0. 9, 9, and 6 is 24. Add 2 more, you get 26. Carry the 2. You have a 2, you need 1 more to get 3. So that other angle is going to be 120 degrees. So the arc, since it's a central angle, if I didn't say it, that's the center. So the measure of arc BC, from B to C, oh, I have that. It's 120. CDA, start at C, go to D, go to A. It's 90 plus 90. Angle BAD, B-A-D. So you start at B, you go to A, and you go to D. Well, that's 60 and 90. That's 150. And CDA, you start at C, you go to D, and you go to A. Well, that's 120 plus 60. That's 180. And it makes sense that if below this is 180 degrees, then the top half will be 180. Or, if you wanted to, CBA. That angle is 120 degrees. The central angle is 180. Therefore, the arc is 180 degrees. Pretty neat. Just add up as you go along. Almost like a perimeter. You have a circle, center O. And you have chord AB, AB, and chord CD. And you were told that AB in length is congruent to CD. Line segment AB and CD, same length. And you want to conclude that the arcs AC and BD are the same. This arc and that arc, you want to show that they're the same. You want to show that they're the same. Okay. Well, let's do this. Now, we don't know that they're the same yet, so let's get that away. So, let me just write down one thing. This is given, and this is what we want to prove. Okay. So now we know that those two are the same. Those two are the same. Okay. Which means those base angles are the same. Now, when it comes to AB, I can do the same thing. I can go like this, and I can go like that. And AO and BO are the same as OC and OD. They are, well, radii. Okay, so basically we have these two triangles. We have OC and D. Those angles are equal, and these two sides are equal to one another. And then we have ABO. ABO. Let me try to draw it somewhat believable to their diagram. And we know that AO and BO is the same as CO and DO. And we know that angle A and angle B equal one another. But we don't know that they equal C and D yet. And we're also given that those. Okay. Now, what we know is this. If two chords, and AB is a chord, and CD is a chord, if the two chords are equal in length, then the central angles are equal. Then the central angles are equal. That is, let's draw it in the same color. AOB and COD are the same. This angle, call it 3 slashes. And this angle, they are the same. Okay. Now, triangle 1, triangle 2, they are congruent. And the reason is SA side angle side. Side angle side. Side with 1 slash, angle with 3 slashes, side with 1 slash. These are the same triangles. Okay, these are the same triangles. Okay. In particular, those angles in the middle are the same. Now, what I'm going to do is, since we have these triangles overlapping one another, that's confusing. I am going to draw, to the best of my ability, 2 congruent triangles. 2 congruent circles. A, B. And here's O. Let me abuse notation and use the same letter, the same name of the center for the other circle. Also O. Okay. Now, what we know is these 4 are equal. And we know that the central angles are equal. The central angles are equal. So what we can say now is that arc CD is congruent to arc AB. Now, there's a point D right here, and there's a point C right here. Point A is right here. Okay. Now CD is really CAD. And AB is ADB. Okay. If I may come in the center here, arc. CAD is equal to arc CA plus AD, plus arc AD. That's CAD. ABD, or ADB, is AD plus DB. But these two are equal. And if I take away AD from both sides, what remains, CA and DB, they're equal. And I'm hoping that's what it says here, and it does. How you name an arc is like a line segment. It doesn't matter which you put first. CA is a C, and DB is BD. So yep, they are congruent. I took away the same from both sides. To be honest, kind of anticipated it was going to be like that. But that does come from a lot of experience. Let us try one more. Suppose you have this triangle. The center is O. You have point A. You have point A. You have point B. You got C and D. A, B, B, C, C, D. A, C, and of course C, D. C, D. All right. And you were told that AC is congruent to BD. And this is given. And you want to conclude, you want to prove that CD is congruent to AB. Okay. Actually, you want to prove that those arcs, CD and AB, are actually congruent. Okay. So, it's this arc, AB, and CD. Well, what I'm seeing is maybe we can show that ABC and DCB are the same, congruent. Take away BC from both sides, and then we get what we want. AB and CD, same length, same arc. So that's what I want to show. Okay. So I'm going to modify the diagram by going like this. You know, we're given that okay, so these two are the same lengths. AC, BD, the same lengths. Oh, they're the same lengths. That means they cut off the same arc. Now the proof is done. This angle, so we have arc, we have chord, and we have angle. They all define the same thing. Let us break this into two smaller problems, or two smaller circles. I'm only drawing them smaller due to lack of space. A goes to C with B in between. And over here, the other diagonal, we go from B to D with C in between. And I am told that AC and BD the same. Okay, so here's the center. Here's the center. These two chords in the same circle, or now congruent circles, those two chords are the same. That means this arc and this arc are the same. ABC is the same measure as BCD. BCD. But ABC is arc AB plus arc BC. AB and then add on BC. But BCD is arc BC and then add on arc CD. Is BC plus arc CD. Take away BC from both sides. And arc AB is congruent to arc, not A, but CD, is congruent to arc CD. And that's exactly what they asked us to show. If this is congruent to that, then that is congruent to this. Like addition, you can switch those. That completes the section on arcs of a circle. 6 theorems. But I kind of reduced it to one. The arc in two congruent circles or in the same circle. If you have two chords, either if the two chords are equal, then the corresponding arcs are, two chords are congruent. Then the corresponding, I forget which I said. If the two chords are congruent, then the congruent arcs are congruent. The corresponding central angles are congruent. If the two central angles are not congruent, then the corresponding chords are not congruent. The corresponding arcs are not congruent. You get all three or none.